Good day, students. In this part, we're going to be reviewing the trig identities. So let's take a look at question number 1. We're to find sine A minus B, given that sine A is 2 over 5, with A between pi over 2 and pi, and cosine B is 4 over 7, with B between negative pi over 2 and 0. Okay, so we need to start off by writing down the identity that can help us determine what we're working with here. So we have to find sine A minus B. So what trig identity are we going to use here? Well, we have the sine in two angles, alpha and beta, separated by minus. So we're going to be using the difference identity for sine. So the difference identity for sine is sine alpha cosine beta minus cosine alpha sine beta. Okay? So this is the difference identity for sine. Let's apply it to this formula right here. So if I apply to this formula, sine A minus B is going to be sine A cosine B minus cosine A sine B. Okay? Alright, so let's see what we have. We're given sine A, we know sine A, and we also know cosine B, but we need to find cosine A and sine B. Those are the two we need to find. Alright? Okay, so we can make a list up here of the things that we have. We have sine A is 2 over 5, and then we also have cosine B being 4 over 7. So we have to find the other two. Okay, so let's start off by let's find, how about we find cosine A first? Now, how do we find cosine A? Well, we can use the Pythagorean identity to find cosine A from sine A. The Pythagorean identity I'm going to use is cosine A equals plus or minus the square root of 1 minus sine square A. Okay? If I plug in the value of sine A in here, I'll have plus or minus the square root of 1 minus sine square A is 2 over 5. So when I square that, it's 4 over 25. If I find the LCD of these two, I'll have 25 over 25 minus 4. So we'll have plus or minus the square root of 21 over 25. Okay, because, 25 minus 4 is 21. And then we can simplify that further into becoming plus or minus root 21 in the numerator over 5. Now, is this plus or minus for cosine? Well, we need to consider the interval that this angle resides in, the quadrant, sorry. So A is between pi over 2 and pi. Let's determine what that is with a sketch using our quadrants. So let's see. We have pi over 2 up here, pi over 2, and this is pi. And this is where angle A resides, okay? This is where angle A is. Let me not put a letter there because that might be confusing. So let me just call this pi. And then we're going to see how we can determine the sine of the angle, okay? So this is the angle under consideration here. And we remember that all students take calculus. This S means that only sine and its reciprocal cosecant are positive in this quadrant. So this is neither both of them, so it's going to be negative. So we can conclude that cosine A is negative root 21 over 5. Okay, let's put that up here. Cosine A equals negative root 21 over 5. Now the next thing we have to find is sine B. Now how do we find sine B? We find sine B by applying the same identity, the Pythagorean identity, but we're going to have cosine and sine interchanged with one another. All right? So sine B, using the Pythagorean identity, is plus or minus the square root of 1 minus cosine square B. Okay? So that's another identity. So let's evaluate what this expression is when we substitute the value of cosine. So it's going to be plus or minus 1 minus cosine b is 4 over 7. So if we square that, it's 16 over 49. Okay, and then if you multiply both sides, you have 49 and 1. And then if you subtract 16 from 49, we get 33. Okay, so this becomes plus or minus the square root of 49. Let me just write it so you see minus 16 over 49. So that becomes plus or minus root 33 over 49. And then when we break it apart, it's plus or minus root 33 over 7. So the question now is it positive or negative? Sine b, that is. So to answer that question, we just have to determine what quadrant this angle lies in, and then figure out what the sign is, all right? So angle B is between negative pi over 2 and 0. So negative angles are determined by rotating clockwise. So this is negative pi over 2, and this is 0. This is where our angle resides. And we know that all students take calculus. What this C means in quadrant 4, where our angle resides, is that only cosine and secant are positive. So since this is sine is not cosine or secant, that means it's going to be negative. So this will be negative root 33 over 7 for sine B. Okay, so we have everything that we need. All right, so let's go ahead and figure out what the answer is. So sine A minus B is equal to sine A. Sine A is 2 over 5, and cosine B is 4 over 7. So let me write it again so we don't forget. Sine A cosine B minus cosine A sine B. All right, so sine A is 2 over 5 times cosine B, which is 4 over 7, minus cosine A. Let's see, where's cosine A again? Negative root 21 over 5. Let's put that in parentheses. Negative root 21 over 5 times sine B, which is negative root 33 over 7. Okay? If we multiply them together, we're going to get 8. Now these two minuses multiply to give you a plus. So let's do this. This is 8 over 35 minus, if we multiply these two radicals together, we just multiply the radicands. It's going to be root 693 over 35. Okay, so that becomes 8 minus, denominator is 35. So let's look at the options that we have. Oh, we can see that the answer is option A because that's the only one with 8 minus. But let's go ahead and show that this reduces into 3 root 77. All right, so let's break that down on the side here. Simplifying radicals, we already know how to do that. Let's see. 3, if you add these digits together, 3 goes into them. So 3 goes here. 3 goes into 693, 2, 3, 231 times. And let's see, 3 plus 1 is 4, 4 plus 2 is 6, so 3 goes here also. Since 3 goes into 6, 3 goes into 21, 7 times. And then 21, another 7. 7 can be broken, 77 can be broken down into 7 times 11. All right, so these two repeat themselves, so we can break out as 3. And the simplified form of root 693 is 3 root 77 because these two stay behind, okay? So we can see that our final answer is 8 minus 3 root 77 over 35 as the value of sine A minus B, all right? Which is option letter A. All right, let's take a look at question number 2. This involves the use of the unit circle or the knowledge of the value of your trig ratios. So let's evaluate cosine pi over 12. Now there are two ways of doing this. You can work with radians, or you can express it as degrees. Okay, I'm going to work with radians here. So let's go ahead and do that. Cosine pi over 12. Now cosine pi over 12 is an uncommon angle in the sense that this is an angle that does not show up on your unit circle. So can I express this as a sum or difference of two common angles? All right, so let's work with pi over 12. So I'm going to pick two numbers, multiples of pi that add or subtract yield pi, and have a common factor, or our factors, with 12. So we can use 4 pi minus 3 pi, and both of them go into 12 over 12. And then we can reduce this into 4 pi over 12 minus 3 pi over 12. Okay, and then reduce this becomes pi over 3 minus, and this becomes pi over 4. All right, now this is 60 degrees and this is 45 degrees. So if you wanted to use degrees, this would be 15 degrees, and then you can just use 60 minus 45. It makes no difference. All right, so we know what we are doing now. We have cosine pi over 12 is equal to cosine pi over 3 minus pi over 4. Okay? All right. Now, we're going to determine what identity we're going to be using here. So since there's a difference and there's a cosine, we're going to be using the difference identities for cosine. So cosine alpha minus beta, if you remember what it is, it's cosine alpha cosine beta plus sine alpha sine beta. So for the cosine difference identities, the trig pairs are the same, cosine and sine, and the sine is opposite. All right. So if I apply that here, I'm going to have cosine pi over 3 cosine pi over 4 plus sine pi over 3 sine pi over 4. All right. Now we're going to take a look at our unit circle. Okay, if you remember what it looks like, that's fine. We have two angles here, alpha. Alpha is the first one. Alpha is pi over 3, as you can see here. And beta is pi over 4. Now the unit circle, pi over 3, has x and y coordinates. The x coordinate for pi over 3 is 1/2, and the x coordinate is 1/2, and the y coordinate is √3 over 2. Okay, and then for pi over 4, it's √2 over 2 and √2 over 2. All right, so now let's see what we can do here. We can break them up. So we can partition it like this. All right, so what we have right here is this little trig table of trig identities. So the x coordinate we know is cosine, and the y coordinate we know is sine. All right, so we can use this little chart of common trig angles to find out what these the value of these expressions are. So let's go ahead and apply it. Cosine pi over 3 is the x coordinate of this, which is 1/2. Cosine pi over 4 is √2 over 2. As you can see here, cosine pi over 4 is √2 over 2, plus sine pi over 3 is √3 over 2, and sine pi over 4 is √2 over 2. If you multiply this together, you have √2 over 4 plus √6. You multiply the radicands here, 3 times 2, and then 2 times 2 in the bottom, 4. And as a combined fractional expression, we have √2 plus √6 over 4. And that's your final answer, option letter D. All right, let's take a look at question number 3. We're to find the identical expression for the following: cosine square x times tan square x plus 1. So we're going to be making use of multiple identities here. First of all, let's take a look at this identity right here, tan square x plus 1. If you think about your Pythagorean identities, do you remember what tan square x plus 1 is? From the Pythagorean identities, tan square x plus 1 is equal to secant square x. So if I apply that here, I'm going to have cosine square x. Let's write that again. Cosine square x times tan square x plus 1 is equal to cosine square x. Now instead of tan square x, I'm going to write times secant square x parenthesis. Now we're going to use another identity known as the reciprocal identity. If I apply the reciprocal identity to secant, what do I get? You recall that secant x is equal to 1 over cosine x. So if I square this, I'll just simply square 1, which is 1, and then I'll square that also, okay? But the original identity is secant x is equal to 1 over cosine x. So if I apply that here, this will become cosine square x times 1 over cosine square x. Now you notice that I can reduce this, divide this by cosine square x, and that cosine square x, these two cancel out, and our final answer is 1. We can see that option C is our correct solution. Now let's take a look at question number 4. We are to find the values of the inverse sine of negative 1/2. And we have multiple responses here, multiple answers here. There are different ways we can do this. If we have memorized our reference angles, we can use that. We can use a unit circle, or we can also make use of the calculator. Okay, so I'm going to use a calculator to show you how to figure out what this is. Okay, so if we say some angle theta is equal to the inverse sine of negative 1/2. What does that mean? This follows that if I take the sine of both sides, I'll have sine theta, sine of theta is equal to sine of the inverse sine of negative 1/2. This follows that on the left side, sine theta is equal to negative 1/2. So all these theta values, if I take the sine of them and get negative 1/2, then they satisfy this equation, this expression right here. Okay? All right, so let's write down the expression I'm going to be plugging into my calculator. I'm going to be looking for sine of 30 degrees, sine of 330, sine 30, sine 330, and then sine 390, sine of negative 30, sine of 150, and then sine of 210. All right, I want to see which one yields negative 1/2 as an output. Now you have to be careful. You have to ensure that your calculator is in degree mode before you start your computations. All right, so you can see DEG here with my TI-89 titanium is already in degree mode. If not, you just go to mode and change it. All right, so let's go ahead and do this. We have sine of 30 is 1/2, no good. Sine of 330, negative 1/2, that's good. Sine of 390, 1/2, that's no good. Sine of negative 30, negative 1/2, that's good. So let's write down what we have so far so we don't lose track. So we have for 30 degrees is 1/2. This is negative 1/2 for 330. 1/2 for 390, negative 1/2 for negative 30. So bottom line, we know that this is good, this is good, and these two are no good. All right, let's try the last two. Sine 150 and 210. All right, let's look at 150. Sine 150 is 1/2, no good. And then sine of 210 is negative 1/2, and that's good. All right, so this is 1/2 right here, which is bad, and negative 1/2. All right, so our answer, solutions, are A, C, and I'm sorry, our solutions are B, D, and F. All right, so let's cancel this out. Solutions are B, option B, option D, and option F. Another way you can do this is by using reference angles, as I indicated earlier. In order to do that, you have to be able to see that the reference angle for all these indicated angles are in fact 30 degrees. Okay, and then you know that all students take calculus, and the only quadrants where sine has a negative value is either in quadrant 3 or quadrant 4. So any of these angles that reside in quadrant 3 or 4 are going to be candidates by default, since they all have a reference angle of 30. All right, so 330, we know it's right here. Reference angle of 30 is in quadrant 4, so it's good. Negative 30 is right here also, so it's good. And 210 is right here, reference angle of 30. So we have 210 right here, and then we have 330 or negative 30. Okay, so since this is tan and cotangent, and this is cosine and secant, sine is going to be positive in these two angles right here. Okay, the other angles that we have, 30 is over here. This is 30 degrees, or is also 390. Sine is positive here, so that's no good. And then the other angle we have is 150, and that's over here. And we know that sine is positive here also, so that's why it's no good. So if you know your reference angles, and all students take calculus, you can also use that to determine the right solution. Okay, now let's take a look at question number 5. This is a multiple response question. We're to find the identical expression for the following: sine t divided by 1 plus cosine t. Okay, so let's write it down. Sine t divided by 1 plus cosine t. All right, so we know an identity that involves 1 and cosine. It's of the form 1 minus cosine squared t equals sine squared t. So can I multiply this by a certain factor to get this? The answer is absolutely yes. Think about your difference of squares. If you have a plus b, what do you multiply it by to get a squared minus b squared? You multiply it by a minus b, right? So if you have 1 plus cosine t, to get 1 minus cosine squared t, which is an identity we can substitute with sine squared t, because this is equal to sine squared t. What I'm going to do is I'm going to multiply the top and the bottom by 1 minus cosine t. 1 minus cosine t, 1 minus cosine t. All right? On the top, I'll have sine t times 1 minus cosine t. And on the bottom, you already know what you're going to have, right? If this is a plus b and a minus b, is going to be a squared minus b squared, or 1 squared, which is 1, minus cosine squared t. Okay? Let me show you the steps so that you can see what I'm talking about. So if you fold this out, first, outer, inner, last, you're going to have 1 first, outer minus cosine t, inner plus cosine t, last minus cosine squared t. So you notice that the two terms in the middle cancel out, right? So we now have sine t times 1 minus cosine t over an identity that we know, 1 minus cosine squared t. So 1 minus cosine squared t is equal to sine squared t. We can make that substitution here. So we have sine t times 1 minus cosine t over sine squared t. Okay, if we freeze for a minute, we'll find out that we've had a match. All right, option B is an identical expression to this expression right here. Okay, well, let's go ahead and simplify it a little bit more to see if we can get more matches. Let's see. Oh wait, we can break this down. This can be written as sine t times 1 minus cosine t divided by sine t times sine t. Okay, so this sine t's cancel out. So 1 minus cosine t over sine t is what we'll be left with. 1 minus cosine t over sine t. Okay, and this matches with option letter D. Okay, now all right, let's take a look at question number 6. Question 6 says prove the trigonometric equation, identify the property or identity used in each step. All right, so let's take a look at this. So first thing we can notice is that this quantity is being squared, cosine minus sine x. So this quantity is being squared, we can express it as cosine x minus sine x times what? Times itself. That's what squaring is, right? Times cosine x minus sine x minus 1. Okay? The question is it equal to 2 cosine x sine x? All right? Now, what we're going to do next is distribute. Okay? So let's distribute this out. First, outer, inner, last. So if we do the first, it's going to be cosine square x, outer, minus cosine x sine x, inner, minus sine x cosine x, but using the reflexive property of multiplication, I can write that as write this as cosine x sine x. Okay, so that's inner, and then last will be minus times minus plus sine square x minus 1. Is it equal to 2 cosine x sine x? All right, this right here is a distributive property that we just applied, so we can put it right here, distributive property. Okay, now let's simplify. The middle terms cancel out, so we're going to have cosine square x plus sine square x. Actually, they don't cancel out. We can actually combine them, right? So if I combine these two, it becomes negative 2 cosine x sine x minus 1. Is it equal to 2 cosine x sine x? Now, does this look like an identity that you can recognize, cosine square x plus sine square x? Absolutely, they add up to 1, right? So this is 1, 1, minus, we can now move this 1 right here. 1 minus 1 minus 2 cosine x sine x. Is it equal to 2 cosine x sine x? Okay? So what we did up here was just addition. And then here we use the Pythagorean identity. Or yeah, we can just call this operation subtraction. it's kind of related to addition, but what we did is we subtracted these two right here. So subtraction, subtraction. All right, well, we're combining this term and this term. All right, now if you combine these two terms right here, you notice 1 minus 1 adds up to 0. So you have negative 2 cosine x sine x. Is it equal to, kind of drop the minus, is it equal to negative 2 cosine x sine x, as indicated earlier? And the answer is yes. So that completes the proof. All right, let's take a look at question number 7. So question 7, if cosine theta is 3/4 and theta terminates in the first quadrant, find the exact value of tan 2 theta. Okay, so we're going to start by writing down what the identity for finding tan 2 theta is. This is going to be the double angle identity for tan. So we have tan 2 theta. There are different variations of them. The one I'll use, I'm going to use sine 2 theta divided by cosine 2 theta. All right, so to figure this out, I'll just find sine 2 theta and cosine 2 theta, and then divide them by each other to get tan 2 theta. All right, let's start with sine 2 theta. To find sine 2 theta, I'm going to use the double angle identities for sine, and that is 2 sine theta cosine theta, 2 sine theta cosine theta. For this one, we already know what cosine theta is. Cosine theta is 3/4. So what is sine theta? Can we find it? The answer is absolutely. If we know cosine, we can find sine using the Pythagorean identity. So we can use the identity sine theta equals plus or minus the square root of 1 minus cosine square theta. So plus or minus the square root of 1 minus cosine is 3/4. If you square that, you get 9/16. And this becomes plus or minus the square root of 16/16 minus 9/16. When you look for the LCD of 1/1, subtract the numerators, you have plus or minus the square root of 7/16, which is equal to plus or minus root 7/4. Okay? Now, the question is it positive or negative? Well, since theta terminates in the first quadrant, what does that tell me about the sign of sine? So we'll make our nice little quadrants right here, coordinate system. And we know this is where theta resides, and we know this is where a is. A means all 6 straight functions are positive. So we can conclude that sine theta is equal to positive root 7/4. Okay? Now let's we now know sine theta is this, and then earlier it was indicated to us that cosine theta is 3/4. So we're ready to compute the value of sine 2 theta. So sine 2 theta is going to be 2 times sine theta, which is root 7/4, times cosine theta, which is 3/4. Okay, you have to be careful multiplying here. 2 and 3 are integers, so you multiply them together. 6, and the radical stays alone. Root 7 divided by 16. You can divide the top and bottom by 2. 2 is a common factor. So this becomes 3 root 7/8. So there goes the answer for sine 2 theta. Now let's find cosine 2 theta real quick, and then we'll be good to go. Cosine 2 theta is, there are 3 variations for cosine 2 theta, but since we're given cosine theta, I'm going to use the identity that is dependent solely on cosine for accuracy reasons. So I'm going to use the identity 2 cosine squared theta minus 1. So that's going to give me 2 times cosine theta is 3/4 square minus 1. Okay, so we have 2 times 9/16 minus 1. Simplify this. 2 goes here 1, 2 goes here 8 times. So we're going to have 9/8 minus 8 over 8, which equals positive 1 over 8. Alright, so now we have sine 2 theta and cosine 2 theta. So tan 2 theta, you have to be really careful here. Tan 2 theta is sine 2 theta over cosine 2 theta. Alright? Because we have sine theta and cosine theta, that's not what we're using here. We're using the sine 2 theta and cosine 2 theta to figure out what tan 2 theta is. Alright, so sine 2 theta is 3 root 7 over 8, and we'll divide that by 1/8. So to do this, we'll multiply the numerator by the reciprocal of the denominator. Okay, so the 8's cancel out. And our final answer for tan 2 theta is simply 3 root 7. Alright, so that's that. Alright, let's take a look at the last one, question number 8. We're to evaluate tan of the inverse cosine of 8 over x. Okay, so we can look at this argument of our tan function as an angle theta. Okay, so let's say theta is equal to the inverse cosine of 8 over x. Okay, so if theta is equal to the inverse cosine of 8 over x, what do you think these two measures are in a triangle in standard position? So let's make a triangle in standard position right here. I'm going to put it in the first quadrant. Okay, and let's say theta is in quadrant number 1, since there's no negativity here. So this is theta right here. So this is going to be your opposite. This will be your adjacent. And this will be your hypotenuse, right? Hypotenuse is opposite to 90 degrees. Opposite is opposite to theta, and then adjacent is the other side. Now you remember from SOHCAHTOA that there's a special relationship that cosine has, right? So cosine is the adjacent over the hypotenuse. All right, so here we know for a certainty that this piece right here is the adjacent, and this is the hypotenuse, 8 over h, because inverse cosine and cosine work hand in hand. Let me prove that to you right here. If theta is equal to the inverse cosine of 8 over x, that follows that if I take the cosine of both sides, cosine theta is equal to 8 over x. So we can clearly see that this is adjacent, and this is hypotenuse from SOHCAHTOA. Okay? Alright, so the adjacent is a constant 8. The hypotenuse is a variable x. We asked to find tan. What does TOA tell us about tan? Tan theta is opposite over adjacent, right? Over 8. So we know what the adjacent is. We need to find the opposite. Now, how do we find the opposite? We just simply use the Pythagorean theorem, right? So I'm going to use the trig variation of the Pythagorean theorem. Adjacent square plus opposite square equals hypotenuse square. Alright, so let's plug in what we know. We know that adjacent is 8 squared. Opposite, we have no idea what that is. And the hypotenuse is x squared. Now let's go ahead and isolate O. O squared is equal to x squared minus 64. And O is equal to the square root of x squared minus 64. So that's our opposite right here, right there. Okay, so let's go ahead and put everything together. So tan theta, which is equal to, we remember what we call theta, right? Theta is this expression right here, which is tan of the inverse cosine of 8 over x. That is equal to opposite over adjacent. Our opposite is root x squared over 64, and our adjacent is 8. Alright, so that goes our final answer. X squared, the square root of x squared minus 64 divided by 8. Okay, so that's that. Thanks so much for taking the time to watch this presentation. You can feel free to subscribe to my channel, and please post a comment to let me know what you think about this clip. More clips can be found on mathgoodserve.com. Thanks again for watching, and have a wonderful day.